Okay, so this is joint work with Olaf and Luke, who's in the audience. It's work on proof complexity of quantified Boolean formulas. Okay, there's a lot of things that I would like to say about this paper and a lot of stuff that I want to tell you about, but inevitably I'm going to have to be selective because there's only 20 minutes. So what I'd really like to do is explain how this technique works, what it does, and how we apply it. That's the main thing that I would like to do, but I also think it's important that I give you some context. Okay, so I'm going to start here. So proof complexity is a field which has kind of recently emerged as the theoretical counterpart to practical solving. And this is perhaps best illustrated with SAT solving, which is probably the simplest case. So what happens is if you start off outright with an unsatisfiable formula, and you give this to your SAT solver, the solver in some way has to show that none of the assignments work. And this means that the trace of the solver can essentially be interpreted down here as a proof of falsity, or a proof of unsatisfiability, rather, in some proof system. Now, these proof systems, generally the ones we work with, are quite nice and neat and tidy, and they're very amenable to analysis. So this picture is quite pleasant, and it really means if we have some lower bounds on proof size over here, this gives us a kind of best case scenario for running time of the algorithm. Okay, also, if we have a lower bound on some other measure which is called proof space, this gives us best case scenario for memory consumption. So proof complexity is a tool with which we can analyze the potential and the limitations of solving methods and also compare them. Okay, now there are a whole bunch of propositional proof systems available. These are just 4 of them. Okay, so resolution down here is the one that underpins the state of the art in SAT solving. Very well-known and well-studied system. Cutting planes as well on the left, which is based on linear inequalities. Here we have polynomial calculus, which is based on polynomials. And at the top we have Frege, which is the kind of standard textbook system for propositional logic. Now, what all these systems have in common is that they're line-based. Okay, so it means your proof is a sequence of lines. Okay, you get some axioms for free, lines you can introduce under no assumptions. Then you have some logical rules with which you can combine lines to get new ones. And your target is some line which represents, in this case, trivial falsity. Okay, so in the case of resolution, this line is the empty clause. Okay, it's empty, it can't be satisfied by any assignment because it has no literals in it. So these are the kind of proof systems that we'll be working with. However, we want to be in the realm of QBF. Okay, so as Celio mentioned, a QBF here is just a proposition, but it's prefixed by this quantifier prefix, which is a sequence of quantifier blocks. Quantifier followed by a set of variables. In this case, they're all singletons. The main thing on this slide that I want to get across to you is if you have an existentially quantified QBF here, okay, this is essentially equivalent to a SAT problem for obvious reasons. I mean, this is just saying there exists an assignment such that this formula is satisfiable. Okay, it's just equivalent to a SAT instance. This means that since SAT is nested within QBF, whenever we study QBF proof complexity, we're inevitably studying propositional proof complexity as a special case. Okay, and that's something which will be significant later on in the talk. Here's an example of a core system, proof system for QBF. It's called QU resolution. This is historically what it was named. But it might as well be named, or you could think of it rather, as resolution plus universal reduction. Okay, where this universal reduction rule is something that we're going to add to lift this from a propositional system to a QBF system. Okay, so we have axiom rule, you can introduce a clause from the matrix. Resolution rule, this is just propositional resolution. And this extra rule here, so what I want to draw your attention to. So this says that if I have a clause, and I have a universal variable in this clause which is innermost, and that means that it's quantified after all the other variables in the clause, then it can just be dropped. You just get rid of it from the clause. Okay, this rule is needed for completeness. Otherwise, you just got propositional rules and you can't prove, or you can't refute false QBFs. So this is a rule we add to make the system complete. And in a nutshell, what universal reduction is doing is just assigning innermost universals, right? That's the message I want to get across here. It might not look like that's what's going on, and historically that's perhaps not what was understood as going on, but if we think that that's what's going on, this gives us a very natural thing which will generalize. How does it generalize? Okay, we have a general for all reduction rule in which in any line-based system, if I have a line and I have an innermost universal variable, then I can just assign it. So this works for any natural line-based propositional proof system P. So under some very weak conditions on this line-based system, then this rule will apply. And by applying it, so just taking P and adding universal reduction, we get a system called P plus for all reduction. And this thing is sound and complete for QBF. And these are the systems to which our lower bound technique is going to apply. Now, one thing about this system, which we need to be aware of, is that hardness results from the propositional domain will lift immediately to this system. Okay, anything that's hard for P, so if I have this family of formulas, 5n, is hard for P, then we just quantify them existentially, and they're going to be hard for P plus for all reduction. Now, whereas this definitely gives us a valid lower bound, it's perhaps not the phenomenon that we want to study. Okay? We're certainly interested in lower bounds that come from alternation, okay, and the existence of universal quantification, and we're interested in figuring out what kind of lower bounds are in existence that don't just come from propositional proof complexity. Okay, so we introduce this, well, we don't introduce this, but we'll use the notion of genuine QBF hardness. Okay, now in a nutshell, in P plus for all reduction, this just means count universal reduction steps. Right? It's P plus for all reduction. P is a propositional stuff, so if we don't count those inferences and just count universal reduction, we can be 100% certain that the lower bounds we're dealing with are genuine. Okay, they're not coming from propositional proof complexity. This notion can be made precise by allowing NP oracles in your QBF proofs. Okay, but we don't really need to digest those details. Just remember that what we're talking about is counting universal reduction steps. All right, so in this talk, develop a new technique for genuine QBF lower bounds, and it's going to apply to all P plus for all reduction systems, right? So whenever we have P and P plus for all reduction is defined, then this technique will give you an absolute lower bound on proof size. Right? It might not necessarily be exponential, okay, but in certain concrete and interesting instances, it is. The technique itself is semantically grounded. Okay, it exploits this notion of this paradigm, if you like, of strategy extraction, which is a well-established thing in the world of QBF. Then I'm going to give you some applications. So I'm going to introduce some new formulas, which are called the equality formulas, which are a nice new lower bound family for QBF, which is nice to have because we don't have so many lower bound families there. And these are structurally quite simple. And then the final application, which is, well, the major application really is to the first genuine lower bounds for random QBFs. And this will apply in the QBF analogs of resolution, cutting planes, and polynomial calculus. All right, so lower bounds from strategy extraction. Okay, so we have a two-player game in QBF, which is a really, really nice way of interpreting the semantics and is quite useful, I would say. It's certainly very nice to work with. And then we have this paradigm of strategy extraction. So from a proof, we can extract a strategy. Now, formally, what this means is that you can define some kind of polynomial time algorithm on the proof which computes the strategy. Okay, but we don't really need to formalize that this morning. We can just imagine that the existential player is choosing moves and the universal player is responding to them, such that they will always win the game for every choice. So, somewhere nested within the proof are all these responses. Okay, and we just need to figure out a way of extracting them. And given an existential choice, what's the matching response? Okay, and that's basically what strategy extraction is doing. And what we're hoping for here is that short proofs will lead to easy strategies. Okay, or contrapositively, if we have complex strategies, then this is going to necessitate large proofs. Okay, so one of the insights in this paper was this notion of a response map. So this is an object or a function which we introduce in order to formalize strategy extraction in the general sense of P plus for all reduction. Okay, but we want to formalize it in such a way that we can kind of pluck out this lower bound technique. Now, previous incarnations of strategy extraction were using a response map, okay, but it was fixed, and it was being used implicitly. So what we've figured out is that strategy extraction can be defined with respect to an arbitrary response map, and this gives us an extra degree of freedom. Okay, and it's really this which allows us to develop this lower bound technique. So a response map looks like this. Here's the function. L is a line in your P+4 reduction proof. Alpha is a total assignment to the existentials, and beta is a total assignment to the universals. And the function has a property that if the restriction of L by alpha is not a tautology, then the restriction of L by alpha and beta is false. What this really means intuitively is, and if the line is falsifiable, then it gets falsified by the response from the response map. So for example, in resolution where the lines are just clauses, the obvious way to falsify the line whenever it's falsifiable is just to assign the universal literals to be false. Okay, the universal player has a very easy way of constructing a response map here, and this demonstrates that, in fact, in resolution, the response maps are very, very simple. In fact, they're actually independent of the choice of existential move. Okay, and that's something which is very important going forward and how this technique applies to the particular case of resolution. Okay, so we define a response map so we can formalize strategy extraction. I don't really have to give you these details, I don't think, so we'll just skip them. Another reason that we define this response map is to define something which is called capacity. Okay, so this is cost and capacity, the two measures that we'll be using to determine these lower bounds. Capacity. This gives us an upper bound on the number of responses that will be extracted per line. Okay, so the proof itself has all the responses in there, and we're going to extract all of them. And this is saying, given a line, you're only going to get a certain number of responses from that particular line. Okay, so we define this as follows. Let L be a line. The capacity of a line is the size of the minimal range of the response map. So this is where having an abstract definition of a response map comes in handy. The minimum range of a response map over all response maps for the line. Then the capacity of a proof is just the maximum of the capacity of its lines. For example, in resolution, clauses just have capacity 1. So as I said, you've just got an obvious single response which works in all cases. So a response map which just uses one response. So resolution proofs always have capacity 1. That's a nice proposition to have. Okay, and what we want to do is marry this up with something which gives us a lower bound on the total number of responses that will be extracted from the whole proof. Okay, so we make a definition which is called cost. Fix a winning strategy S for a QBF, and then consider the size of its range in each universal block. Okay, not across the whole formula, but restricted to a single universal block. And the cost of the formula is the minimum of this range over all winning strategies. Okay, so what this means is, intuitively, if the cost of phi is C, and you give me some winning strategy for phi, then I can point you to a universal block which has at least C responses in it for the strategy. Okay, so here's an example of how you will compute cost, and also an example of formulas which quite clearly have an exponential cost, and these are the equality formulas, which are the new formula family that we introduce as hard formulas for QBF. Nice to have these because, I mean, we don't have so many formula families that are lower bounds in QBF, and these are pretty simple things. So, I mean, without passing this whole thing, the salient feature of these formulas is the only thing that the universal player can do to win is to copy on this block, as his assignment, what was played on this block. N variables per block, so it means these formulas have one universal block, they have a unique winning strategy, and it contains exponentially many responses, so the cost, almost trivially, has to be 2 to the n. Okay, nice formulas, high cost. All right, now we can put all of this together, and this is the main theorem which constitutes our low bound technique. So this is the size cost capacity theorem. States that for each P plus for all reduction proof pi of a QBF, the size of pi is at least the cost of the instance divided by the capacity of the proof. So if I've done my job okay, it should be clear why that is. And also that this gives us a lower bound actually on the number of lines. Okay, number of lines is not always precisely the definition of proof size in a system, but it's important to notice that we get a lower bound on the number of lines. First example of how to apply this theorem is with the equality formulas. Their cost is exponential, the capacity is unit, so you plug these guys in for Q resolution, the capacity is unit. Then the proofs must be of exponential size. Okay, there's no hidden omega here either or anything, it's absolutely at least 2 to the n. Some remarks. This is a semantically grounded lower bound technique, which is nice because techniques of this flavor, if you like, have more chance of kind of being general rather than being based on the syntactical form of a particular system. It's based on the syntactic properties, semantic properties rather of the instance, and that's something which is useful. This works regardless of whichever base system P you choose. It may not always give you an exponential lower bound, but it gives you some absolute lower bound. Okay, and also it always produces these genuine lower bounds, which I mentioned earlier. Okay, this is true because whenever you extract a response, it's actually from a universal reduction line. Okay, the propositional lines, inferences in the system don't affect the strategy, which makes perfect sense because they're logically correct propositionally. So it always gives us a genuine QBF lower bound. So you know whenever you obtain a concrete lower bound using this technique, it's not interfacing whatsoever with propositional hardness. How does this work for some other systems? Just quite briefly. Well, for cutting planes, we can prove the capacitive lines is still 1. In a nutshell, this works because lines in cutting planes being linear equalities are representing threshold functions, and it's just quite clear, really, how you would pick a response which always minimizes the left-hand side. Corollaries, well, if you put this capacity being 1 into size cost capacity, then you find, well, the size of proofs here is lower bounded by cost alone. Okay? Capacity is just vanishes from the inequality. This, of course, means that the equality formulas here are still hard. Moving on to polynomial calculus, which is a more interesting case. Here you have a greater expressivity in the lines, as that's what this example is showing, but I won't talk about that in detail. But we have this really nice lemma which says that the capacity of a line in this proof system is bounded above by the number of monomials. You need some linear algebra to prove this. It's a really nice lemma. And then, in this proof system, the size is actually determined by the number of monomials. So it works out that here, the square root of cost is giving you an absolute lower bound on proof size. Okay, so the equality formulas are hard even in this system. Okay, and given that this system is incomparable with cutting planes, it's very nice to have a technique which gives you those 2 lower bounds in one shot, because you can't derive one from the other. Finally, just very briefly, just coming to the end now, this final application is to hard random formulas. So we have a model of random QBFs where we pick some clauses uniformly at random. And we do this by selecting 2 literals from a set of existentials and 1 literal from a set of universals. This is a known thing that you do in QBF because it's basically to avoid having a fully universal clause, which would give you a false formula immediately. And then we build this formula here, which has a sigma 3 prefix. And you may notice that the structure of this is kind of similar to the equality formulas. So it's kind of based upon that structure, but with these clauses generated uniformly at random. And then if we select these parameters very carefully, with C and M was a number of universal variables, we can prove with high probability that the random formula is false, and it requires exponential size proofs here in Q resolution, cutting planes plus Fourier reduction, and polynomial calculus plus Fourier reduction. Very quickly, the proof idea here is that the formula itself is false if and only if all these psi I subgames are also false. Okay? And we can show that these are false with high probability. To do so, we use a reduction to random 2-sat and some results in the literature there. We can also show that they have non-constant winning strategies with high probability. There's a nice little trick to showing that. But in tandem, these 2 things imply that the formula is false and actually has exponential cost. Okay? Then we can apply size cost capacity, and we prove that these formulas are hard in these 3 systems with high probability. That's a proof sketch, which I should probably skip. But yeah, you can check the paper for the details. So in summary, QBF versus propositional proof complexity is different. Propositional proof complexity is nested therein, but we want to figure out what other stuff is going on. We introduced this new semantic technique for genuine lower bounds, which applies across the board for P plus for all reduction, yields these genuine lower bounds. And our major application here was in versions of resolution, cutting planes, and PC, QBF versions to show that these random formulas are hard there. Just remains to say thank you for listening. Thank you. Yeah.
In your applications, you use formulas that have QBS formulas that have very few
Very good question. Certainly difficult is with the unbounded case. Certainly more difficult to show lower bounds with this technique on unbounded formulas. But if you look in the paper, which is something, as I said, I had to be selective about what to present, there are a very famous bunch of lower bound formulas in QBF called the Kleiner-Booning formulas, which are of unbounded proof, quantifier complexity. And in fact, if we do some reductions by kind of shifting things around, we can actually use this technique to prove that they are hard. And in some way, we are using the structure of the formulas, so we don't know if this is a general technique or not. But that's definitely something that we're working on with the unbounded case. Yeah.